Hello, thank you for watching our contribution to the ICRA 2020 virtual conference. The title of this work is Accelerating the Estimation of Metabolic Cost Using Signal Derivatives, Implications for Optimization and Evaluation of Wearable Robots. This paper is published in the March 2020 issue of the Robotics and Automation magazine, and we're excited to present this work to the ICRA community through the RAM to ICRA initiative. My name is Kim Ingram. I'm a graduate student at the University of Michigan, and this work is done with my advisors, Elliot Rouse at the University of Michigan and David Remy at the University of Stuttgart. A chief goal of many lower limb assistive robots, for example, the exoskeletons pictured here, is to augment the user's motion in a helpful, intuitive way. Because of this, a common evaluation metric for these systems is the effect of the robotic assistance on the metabolic cost of the user. Metabolic cost can be used as a physiological cost function in a process called body-in-the-loop optimization. This process requires that the user wear a robotic assistive device, where the actuation profile of the device can be any parameterized assistance trajectory, and commonly this trajectory is device torque or power as a function of the gait cycle. While the user walks with the current assistance profile, their metabolic cost is measured or estimated. And given the metabolic cost associated with that setting, an online optimization algorithm chooses the next setting to test. This process continues, eventually converging on the optimal actuation profile that minimizes the energetic cost of the user. A challenge with this method, however, is that body-in-the-loop optimization algorithms require real-time estimates of metabolic cost, and these are currently obtained through indirect calorimetry. Some of the challenges associated with indirect calorimetry is that measurements are noisy, sparsely sampled, and they require that the user wear a bulky mask over their nose and mouth. These signals are also dynamically delayed. For a step change in activity intensity, say for example changing walking speeds, there is an associated step change in metabolic effort, which we call our ground truth energy cost. But using indirect calorimetry, it can take approximately 6 minutes to get a good estimate of this ground truth value. As an alternative, we can use physiological signals collected from portable wearable sensors in order to estimate this ground truth energy cost. Now, this method has the potential to make faster predictions as well as do so without the bulky, obtrusive equipment. In our previous study, published in the Journal of Applied Physiology, we used physiological signals collected from portable wearable sensors in a linear regression algorithm to predict steady-state metabolic cost. Some of the most important signals we used were heart rate, minute ventilation, and limb accelerations. However, with this approach, we noticed that the speed of obtaining an accurate estimate of ground truth metabolic cost was limited by the dynamics of the input signals. For example, heart rate and minute ventilation both have been modeled as first-order systems with longer time constants of 58 and 53 seconds. In the current study, in order to improve the speed of estimation, we developed a mathematical framework which leverages the structure of a first-order model, as shown here. In this formulation, tau is the time constant, x is the output, and y is the input. Solving for the model output x requires just a rearrangement of terms, and in this form, we can focus on the linear nature and restate the output as a weighted sum of input measurements. More generally, this coefficient vector can be represented as beta, which we could identify using a pseudo-inverse. Now we see that this form resembles that of a multiple linear regression. In our study, the output is ground truth energy cost, the input signals are the physiological signals and their derivatives. The goal of this study is to evaluate the effect of including signals derivatives on the predictive accuracy of multiple linear regressions that have been trained to predict ground truth energy cost. We hypothesized that we can increase the speed of predicting ground truth energy cost from physiological measurements by including time derivatives in a black box estimation algorithm. And we also expected this to be especially useful when the input signals exhibited dynamic delays. For our analyses, we used a dataset that we previously collected, which is also available open source. In this dataset, 10 healthy subjects performed various activities, which included level walking, incline walking, backwards walking, running, cycling, and stair climbing at a variety of speeds and intensities for 5 minutes each. While they performed these activities, they were instrumented with 16 bilateral lower limb EMGs, 6 triaxial accelerometers, a heart rate monitor, wristbands that measured electrodermal activity and skin temperature, and a pulse oximeter. Subjects wore the indirect calorimetry system to establish ground truth energy cost. In total, for this study, we analyzed 187 5-minute trials across a wide array of subjects, tasks, and energy levels. As with our previous analyses, we grouped the collected physiological signals into two main subcategories. The local signals, which provide information about a particular muscle or limb segment and vary with the periodicity of the gait cycle. These local signals included the accelerations and the EMG. The global signals provide information about the state of the whole body, and those included heart rate, electrodermal activity, skin temperature, breathing frequency, minute ventilation, and oxygen saturation. Together, the 8 local signals and 8 global signals comprise the 16 combined signals in this study. All the multiple linear regressions we trained had the form E equals Y times B, where E was the ground truth energy cost and B was a coefficient vector. We tested 6 different sets of input signals and compared the results. These 6 regression models contained either the local, global, and combined signals only, or the signals plus their derivatives. We compared the performance between models with and without derivatives for the same signal set. For all models, we performed a 5-fold cross-validation where we trained on 80% of the trials and used the identified coefficients to test on the remaining 20% of trials. We repeated this 5 times until all trials had been left out. One of our main findings was that including derivatives in the regression models improved the magnitude of prediction error. In this figure, time is on the x-axis and represents the duration of a trial, or 5 minutes. Mean absolute error, or MAE, is on the y-axis. For each of the 187 5-minute trials, we calculated MAE as the predicted energy cost subtracted from the ground truth, and averaged over 187 trials. The local signals are shown in blue, global in red, and the combined signals are in yellow. Solid lines depict models that are signals only, and dashed lines depict models with signals plus their derivatives. The main thing that we notice is that including derivatives improved the magnitude of prediction error, especially in the first minute. This effect was most pronounced in the global and combined signal groups, while the local signals were less affected. In the first minute, including derivatives in the regression model reduced the error by 0.48 watts per kilogram for the global signals, a reduction of 32.5%, and reduced the error by 0.31 watts per kilogram for the combined signals for a reduction of 25.4%. The other main finding of our study was that including derivatives in the regression models improved the speed of predicting ground truth energy cost. We looked at the metric decay time, which was defined as the time to decrease to 36.8% from initial error to the steady state error. For global signals, including derivatives reduced this decay time by 12 seconds, and for combined signals, it reduced by 3 seconds. We also looked at the metric of time to 1 watt per kilogram, or how quickly the error fell below a threshold of 1 watt per kilogram. And this threshold was chosen because it represented 10% of the entire range of metabolic costs that users experienced across all the different activities. Now here we see very large time savings, with the global signals reaching 1 watt per kilogram 40 seconds faster with derivatives, and the combined signals reaching 1 watt per kilogram 29 seconds faster when derivatives were included in the regression. So these results show us that simply including derivatives in the multiple linear regressions can be responsible for large time savings when trying to achieve some acceptable error threshold. In our study, we showed that including derivatives improved both the magnitude and speed of predicting ground truth energy cost, especially during the first minute and for global and combined signal groups. We did not see an effect of adding derivatives on the local signal group. The intuition behind this result is that several of the global signals, like heart rate and minute ventilation, exhibit dynamic delays. So adding the derivative information can improve the speed of prediction. In a black box data approach, like the multiple linear regressions we used, we're allowed to add information about a signal's rate of change using the derivative as a feature. And this means that it can be applied to a variety of different signals without having to first identify an explicit dynamic model. Altogether, this work is important because the faster we can obtain accurate estimates of ground truth energy costs from portable sensors, the faster we can iterate through control parameters in a body-in-the-loop optimization scheme. The increased speed and lack of restrictive equipment can help translate these algorithms out of the lab. Thank you for watching.